uh, you know, initially this is the water that we need to feed into the system. So you have this pre-filter. We talked about the pre-filter. If you can remember that, some coarse and finer, pre-filter. What are the effects on our filtration? Filter volume versus pressure requirement. So there is a pre-filter provided here, and then we take it into the membrane system, and these are the membrane modules that you can see. This is a bank of modules that are placed here, and these modules, they, so these membranes are schematically shown here like this. The permeate or the clear water passes through this membrane, and then it gets collected in a common pipe. So this common pipe is called manifold. So this is a manifold. The common pipe is this, and then this common pipe takes this water right into the permeate tank. So now permeate tank, you have also what we can say turbidity meter and particle counter, so that you can understand what is the degree of clarity that you have. Now you also, so after the permeate is taken place, there will be a concentrate, right? So this is almost like this. So this is your membrane, and this is your feed, and you are taking the permeate, but right from here you had the concentrate. So this is the feed, you had the permeate, and this is the concentrate. Okay, so that means the final volume that you prepare. So the concentrate is taken out and it goes out, and it is collected, and it is written here backwash waste, or this is a waste material that we can understand. So this is the waste that we can prepare. Now when you backwash this, you actually close this right here and try to create a high pressure around this so that there is a backwashing is possible. So this is the schematic of diagram, and this is the skid mounted pilot scale uh, study unit. So many times before we get into the real life scenario, we just do a pilot scale study to understand the water characteristics and how this this membrane modules can be arranged and what will be the efficiencies. So in order to kind of fine tune the pressure and the membrane running criteria with the temperature and everything. We try to have this run in different parameters, and after we get the optimum running parameters, then the final final plant scale engineering is done, and then the plant scale engineered material or the design places in the real life scenarios. This is for the microfiltration membranes, and here you do not think, we do not have anything like concentration polarization, something like concentration polarization that we discussed in the morning. It is not actually uh, present in this case. So this is not present in this case. So we do not have to deal with the case that we have, as we increase the flux, there will be lot of gelation on the membrane, and that produces lot of problems for the water to pass through. So here it is, everything is directly related with the pressure, but here in case of this, we also discussed that after a certain time, the pressure requirement is just nothing, is no issue there. Only thing is that the concentration of gel layer is an issue, which actually restricts your value of volumetric flow. And then we also discussed that the value of delta or the laminar layer thickness, it plays a big role. And we also discussed that how to
Is there power problem or what?
Does anybody have sir's contact number or something like we could contact him?
Hello? Is there a problem?
Hello.
Is there a problem?
Yes, sir.
Sir, you were out of team for like 4 or 5 minutes.
I was not here.
Yes, sir. You were out of here. Like you were not in the meeting for
Okay.
4 or 5 minutes.
Okay, so let me problem. So let me restart what I was talking about. Let me uh, okay. So where did I, at what point I was out? Did I talk about continuous system before I was out? Where was I? I was right here.
Sir. Yes, sir. You were talking about this pilot scale testing.
Okay. So pilot scale testing is something which I talked about, and fine. And then normally we do the pilot scale testing, and then we go for the final design, and go for plant scale implementation. On one thing is there is that here you don't have any problem of concentration polarization, because you are just trying to remove the particles in microfiltration, and you are not trying to remove anything, any macromolecule or any colloidal substances. But in contrast with this, the problem of concentration polarization is there when we talk about the ultrafiltration system, where the macromolecules, when restricted by this membrane, they produce a gel layer, and this gel layer thickness is actually very, it affects the flux through the membrane. So you can see that we have this formula here, that after this gel layer is formed, then obviously the pressure through the membrane doesn't have any role to play. You increase the pressure, still you cannot increase the membrane flux. Why? Because the flux through the membrane is now being governed by the gel layer concentration, and the only way you can control the flux is that you manipulate this value of delta, or the laminar boundary layer thickness. Okay. Now we discussed that how to remove this, how to lower this thickness of laminar boundary layer, that put pressure spacers on top of these membrane modules, and so that you can create turbulence in here. Now turbulence can be created also by, if I increase the velocity of flow through this membrane, I can increase the turbulence here also. So with that in mind, we actually look at the ultrafiltration systems. And the thing which I was discussing before getting out is that, let me try to uh, you know have this drawing here, but all these things. Let me just wipe out. Okay. Now here, what we try to do is that so this is just a batch system. We have two types of system: batch system and continuous system. Now let me first talk about batch system, and then we will discuss about the continuous system. Now in the batch system, what happens? There is a feed tank where you put your materials to be treated or separated. You put this in the feed tank, okay, and then what you have is that you have this is the ultrafiltration membrane. So this is the UF or ultrafiltration membrane module that you are having here, okay. So this module can be a tubular module, or can be a hollow fiber membrane, or maybe a plate and frame type of device, or maybe a spirally wound type of device. So whatever it can be, so but the way I have drawn it, you can see that this is a cross flow membrane, because the flow will pass over like this, and some of the flow will convert it into the permeate, and this will be collected like this, and this will be taken out. Now and this, whatever is not permeating, that goes into a loop, comes back to the feed tank, and again it is run like this. So initially, let me draw these things. What happens initially is that you have this, this pump is on, okay, and this pump is off, okay, and here is this valve. This will be closed initially, okay. Now if you have this system, what will happen? The pump is on, the water will continuously circulate in loop in this system, and you will get the permeate continuously out of this system. Now why we actually do like this looping system? Because we need to maintain a high degree of flux across the membrane, or high velocity across the membrane, so that the concentration polarization it is limited, okay. It will happen anyway, but it is limited. Now after we reach a certain degree of separation, then what we do, we now come back and we understand that we are done enough. So we turn off this pump, okay, and we open this valve and we turn it on. So what happens is that you have closed this, you have turned off this pump, and you are just cleaning out your feed tank, because you have already concentrated feed. Because so when this was running earlier, you have collected enough permeate through this. The only thing that you now have is the concentrate, which you now can purge off from the system by operating it like this, okay. So these systems are not used in large systems. This is suitable for small scale operations, just like biotechnology plants, biotechnology, or maybe for pharmaceuticals. These are normally bigger, okay. So this is like batch system, and then if we go back to the continuous system, so this continuous system is almost like this. Now you can, it's almost like this system here. Think that this batch system also can be, adapted to continuous use, but it requires some automatic controls, and can be unreliable in many times. But okay, nowadays this reliability has gone up. So normally, but for large scale systems, we require continuous processes. Now, just have a look at this particular diagram and try to understand what I'm saying. This is one stage feed and bleed system. Now you can see here, this is a feed pump. So this is the feed pump here, and then we have a pre-filter right here, or maybe a micron filter right here. And then what we have is another valve. And then you can see this is, you look into this system, here you can understand this is similar to our, this looping system. Without the feed tank, if you consider this looping system, you see this is similar to this looping system here. What happens? Just look at this looping system right here. So you have this pump which is operating, okay, and then it sends this water. It goes through this valve. Don't look at this valve. It goes through this membrane. It goes past this membrane, and then you collect this. It runs in a loop here, right? So you consider that we are running this loop, continuously, but and also we are generating the permeate from here. So it's almost like this, similar to this loop that I discussed right here. But here, what you are adding a continuous feed, and you are getting a continuous bleed from the system. So you are adding some continuous feed, and you are getting continuous bleed from the system. So that's how you can make it continuous. Yet there will be a lot of recirculation is taking place right here. So now normally, if you put a feed of Q, obviously you will be having some bleed from here. Now normally the amount of water that will be recirculated in this will be 5 to 10 times higher than the feed, 5 to 10 times of Q. Okay, let me write it like this: 5 to 10 Q. Okay, so that will be the recirculation. So this will be in the recirculation mode, and you just feed Q, and you take some bleed, and permeate is created. Obviously, if you look at the system balance, then this is Q1 and this is Q2, and Q equals to Q1 plus Q2. So, but you are looping 10 times of the Q. So why we need to do this? Yes, we need to do this because if we do this, then obviously the concentration polarization is limited right here, because a high volume of water is always passing through the membrane. So the flux across the membrane is pretty high, or the velocity of the liquid across the along the membrane is very high. So you have lower higher turbulence, and you have lower value of delta. So then that is how you can limit your concentration polarization. And so you can have also two-stage system. So one stage is like this, and so this is a one looping system, okay, and you take the concentrate from here, put into another looping system, like this. In 3 stages you have 3 such looping systems, and each stage you are taking out the permeate. So each stage you are taking out the permeate and collecting it, and you are you can have a common manifold through which you can collect all of them together. So this is how you operate this. Now, what is the benefit of one stage or two stage process? So you will be a must to know that we actually require less amount of membrane area altogether if we have like 2 stage or 3 stage process. Normally the 1 stage feed and bleed design is kind of inefficient. Then we use multiple stages, and when we add multiple stages, then difference in concentration between the solution which is recirculating in a stage and the feed solution this difference in concentration is minimized, and that actually helps us to have a better configuration. Now think about that we have a single stage, where the concentration of some contaminant is it was 1%, and now here in here it is living as 8%. So that means you are actually taking out a lot of water from the system. How you do this? So you can make a mass balance here, Q into C here equals to Q1 into 0, because permeate is not considered to have any flow rate, any concentration, because we are removing by ultrafiltration, and plus Q2 into C2. That's right here. Okay, and so you can now see if you now do this Q 2 by Q. Okay, so you can see here. So Q2 by Q is nothing but C over C2, right? And so you have here C equals to 1%, okay, and here it is 8%, okay. So this is 1/8. So you get 1/8 of the Q2 is 1/8 of the Q is Q2, right? So our 7/8 of Q is getting produced as the permeate. So this is how you are doing it. Okay. Now you can understand that this is now if you do this, obviously here what the membrane is seeing, the membrane is seeing 8% solution, because you are bleeding from here. So the membrane is seeing 8% solution, and what is on the other side of the membrane? There is C equals to 0. So the concentration differential is 8% versus 0, right? Now, if you look at this equation, you can understand in this case, your C bulk is 8%. Okay, so your C gel is going to be pretty high, right? Now you ask me if you don't understand any part here. Okay, this is important. And now if you look at this part, what we can do, we can we have, let's say C is going in, and from here you can say the C is like, let's say 3%, and then you can make it 8%, okay, in the next stage. So this is 1% here, C equals to 1%. Now if you do the mass balance again, you will see that here Q2 by Q is nothing but equals to 1/3, right? And you are actually getting 2/3 of Q as your permeate. And in the next stage, when you go, so your membrane is saying, what is the solution concentration the membrane is seeing, because it is saying 3%. So your concentration polarization value will be much less, because if you look at this formula here, this membrane is actually seeing CB is equals to 3%, not 8% as before. Okay, so and in this case, in the second stage, if you write this, you have Q into what is the C here, so this is, let's write Q3, this one, okay, and so Q2 into C2, which is equals to, you have Q3 into C3, because from here, if you say this is Q4, this is also equal to sorry, C4 equals to 0. Okay, so C4 is equal to 0 here because there is no so this is a permeate. So you write this mass balance equation and you getting Q2 by Q3 equals to 3 by 8. So this is how and so if it is 3 by 8, then your Q4 is nothing but equals to 5 by 8 of Q2, right? So this is how you can try doing this, and obviously you can understand that the modules in the first stage operate at a concentration 3%, and so it will have higher membrane flux than the one stage unit, and in the second stage also it will have a higher membrane flux. So normally if you compare between the membrane area here and the total membrane area here, so the membrane area in one stage, and if you compare membrane area in the two-stage process, they have, here the total membrane area in two stages, maybe 60% of a single stage process. So this is what we get, and also as you add on more number of stages, your membrane area requirement will be low, and your fouling tendency, will be much lower in these cases. Now, obviously, there is a trade-off that how many number of stages that we can add versus what is the gain that we are getting. So you can see that each stage, there will be pump and valve that will be adding, and we will be operating these pumps and valves, so energy requirement is higher. So if you save on the membrane prices, but you are also putting a lot more in the infrastructure prices, like pump price and valve price, as well as the operating price is a little more because energy requirement is higher. So there is a trade-off, but again, you can safely add 3 or 4 number of stages, and this is how normally the membranes, ultrafiltration membranes work. Now let me get quickly into these applications. So this application is from a car system. So this is from a electrocoating of car. So you can see these cars are right here, and how this is exactly how they are done. So this process actually evolved in 1960 in General Motors company, and then it was widely accepted and used in all over the world. So they had this membrane problem. No, sorry, they had this problem about wastewater, and what happened is that in this electrocoating paint, this paints are electrodeposited. Now, how they are electrodeposited? See, the metal piece that needs to be coated is actually connected with an electrode of opposite charge to the paint particles. So the paint particles are let's say negatively charged, okay, and these cars are actually positively charged. Now what happens if you now dip this car into car body into this paint tank? Those particles which are negatively charged, they just migrate towards this positively charged electrode and can get deposited on this. So, and as because this is electrodeposition, the deposition is very smooth and very nice, and you can control the voltage and then can have a coating over the interweighted surface of the metal part, and then you take it out, okay, and but you'll have some extra paint that might be there due to surface tension or otherwise. So you take it and then you rinse this extra paint off from this car, and then this car goes for the different other fabrication work in the plant. But what happens is that this rinsed water was actually creating a lot of pollution, and somebody was trying to get a solution to this. Now, of course, these paint pigments are very they are expensive, and that way the company was losing a lot of money. Now somebody came up with this idea that why don't we use ultrafiltration systems for this purpose, and that's how they started using it. See, these paint solutions are now they have started recycling the paint solutions in a way that the excess paint, the ultrafiltration plant takes the paint solution containing 15 to 20% solids and produce a clean permeate containing only ionic impurities but no paint particles. Okay, and this is again sent back to this this operation where we rinse this again, and a portion of the ultrafiltration permeate is bled from the tank and replaced by by fresh water to maintain the ionic balance of the process. So this is how it's a classic example, how you can actually make a pollution control device as well as can get a profit back to the company, because you are actually recycling the paint particles back to the system again. So this is one way, very innovative, and at that time it was very innovative thought, and worldwide people started doing ultrafiltration to not only reduce the pollution but also recover and save the plant from losing a lot of money. So this is from electrocoating of the car, and now this is another example here, which you can see this is from a whey production unit. So here how it is done is that in this whey production, so please have a look at the cheese. So they make cheese, and it's a major application in this cheese industry. Now you look at this diagram. The objective of the two membrane process that is shown here is to increase the fraction of the milk protein. So you can see this is ultrafiltration here and ultrafiltration process. And why we do the ultrafiltration? We want to, so this whey contains 1% of protein, and otherwise if we don't treat it, this goes to the drain, and then there is a lot of biological BOD problem in the water that we produce. So but this contains a lot of protein which is good for the muscle building. So you go to any store where you see muscle building proteins, these are all whey proteins, and these are all recovered from cheese production factories. In the form of whey, they they are recovered from the whey. So what is there is that from the milk proteins, we need to take out the protein fraction from here. So we use ultrafiltration membrane, and ultrafiltration membrane of certain size, and the whole process is it uses ultrafiltration, and we use it in two stages, and the goal is to separate the whey into 3 states. The most valuable is the concentrated protein fraction, that we take it out, and then we have also, the whey has a lot of high lactose concentration. So before we use the whey protein as a concentrate, the protein concentration must be, increased to at least 60 to 70%, on a dry basis, and the lactose content should be as low as possible. So this is how we do it. In the first stage, we take out this protein and take out the protein fraction right here. And as because we cannot go to a very high degree of concentration in one stage, we allow also use the water and make it 2 to 3%, and then can take it to the protein. But the rest of the things, lactose and the water, they are, in the permeate, and then we do something called reverse osmosis or nanofiltration, where we can uh, remove the lactose as a concentrate, and water with some dissolved salts can be also taken out, and then they can be, recycled right here. Okay, and then let me talk about a oil water separation unit. So here we use the emulsified. So this is oil water separation unit. So in many processes such as uh, you know steel mills or rolling mills, where you make the thin sheets of steel, for the car body and other stuff, there we use lot of, oil. So vegetable oil and also metal oils are used for as lubricant. So vegetable oil and mineral oils are used as lubricant, and obviously, there is a washing process and everything, cooling is there. So the oil and water gets mixed. Now, before you dispose of this water, there is a need to, separate the oil and water. And if you can separate the emulsion, from oil, you can, reuse this stuff. So this is one particular diagram to show, how this actually works. So this is the diluted used emulsion that comes here. So this is the start point of this plant, and then it comes to a filter where you actually, floating oils are removed by oil skimmer. So this is oil skimmer or band filter. Okay, and then what you do, you take the emulsion into your process. So first there is a fine filter, which is like a microfiltration to remove some of the particles if they are there, and then you put it into a ultrafiltration unit and, separate this oil and water. So this is the filtrate, which is the water, which can be used as a process fluid, and then the concentrated emulsified oil can be taken back here. This is the concentrate reservoir, and then you try to concentrate this part right here, and there will be a bleed line, which is not shown here. The bleed line will make the, emulsion from here. So, or you can bleed from here also. So you can bleed from here also. Okay, so you can bleed from here. So this is one process, and then this one is from textile, where you use polyvinyl alcohol for your textile production, and this polyvinyl alcohols, are, this PVA, they are synthetic fabric weaving operation, and there is a lot of water and heat recovery that can take place. Now you go through this by yourself, and you will be understanding it. Now I don't really, now you understand how to read these diagrams, and you can be very well conversant with this. Okay, so I'll just leave out for you to look at this schematic and understand how this process actually works. So here, we have to recover the PVA or polyvinyl alcohol from the water. So that is the motto right here that we want to do. All right. And now, see, this is just a diagram of is a photograph of a microfiltration unit. So this is a microfiltration unit in it's a hollow fiber module plant to produce potable water from a well, in UK. Now, so this is 25 mgd, so which is about 40 mld, if I am not wrong. But no, it's about 80 mld. I'm sorry. So this is about 80 mld, plant. So this you can see how compact this stuff can be. And this one, now you can see one of these modules. This is the filtration module. Other things are only pipes. So 80 mld plant in a small place like this. So these are the compactness of these microfiltration modules, and they can be, without any problem, they can operate. Only thing is that you require a little bit more amount of electricity, and that's it. So today I could not make it the time to get into the one example. So in the beginning of this next class, we'll definitely discuss this example. Okay. So any question from what we have discussed today?
So
Yes.
yeah, this filtration in the filtration on ultrafiltration is mostly, I think, used for clean water. It's not applicable for any kind of wastewater, sir.
It is when you talk about clean water, obviously when we talk about this, we use microfiltration for removing small particles, from 0.1 to uh, you know 10 micron particles. So the bacteria and very small particles will be removed by microfiltration. Now, even if the solution looks very clean, but it may have a lot of dissolved solids, right? Dissolved organic particles. So dissolved organic materials like protein molecules can be there. There can be, a small amount of, other stuff. There may be very, macromolecules might be there. So it is not as such, and virus might be there. So it is not as such clean water that we normally tell. This is also having lot of impurities in it. So we can remove those macromolecules or protein molecules or virus molecules in the ultrafiltration device. Now, after ultrafiltration, there are a lot of other stuff as well. So what can be there? There can be lot of other ions can be there. Calcium ion, maybe magnesium ion, maybe other ions which are there in the water. That dissolved ions can still be there in the water, for which we will require nanofiltration and reverse osmosis. So in the next class, we'll discuss about nanofiltration and reverse osmosis, so that ions can also be removed from the water. So does it answer your question?
Okay, okay, yes, sir. Thank you.
Okay. Any other question? Okay. All right. If you don't have any other question, then I'll stop this session right now here, and I will see you guys on Friday. So Friday is actually listed as a holiday. I'm not sure whether I will observe it as a holiday or not. But if you get my invitation in your email, then obviously the class is there. But if you don't get any invitation over email, then you consider that there will not be any class. So so just wait and see whether there is an email that you receive. Okay. All right.
Okay.
So
Okay.
all right. So